Hey everybody. In this example, we're going to understand why we need to restrict the domain of a cosine function to define its inverse. We have the graph of y equals cos of x and the straight line y equals x. Now for every value of x, there's exactly one value of cos of x. So this is a function. This means that the domain is all real numbers and the range is from -1 to +1. But notice something important. Different values of x give the same output. Because of negative pi over 4 is 1 over root 2, and because of positive pi over 4 is the same, 1 over root 2. And because of negative pi is -1, and so is because of positive pi. This means that the function is not 1 to 1. So cos of x is a many-to-1 function. So this means that the inverse of cos of x for all the values in the domain won't be a function, because that would then be a one-to-many. So the only way we can make cos of x into a function is to restrict the domain of cos of x. And the best way of seeing this is if we reflect cos of x in the line y equals x, because we know that inverse functions are reflective in this line. So what we'll do, we'll pick some key points and then we'll reflect them in the line y equals x, and that will give us y equals arc cos of x. So we've got negative pi, -1, negative pi over 2 and 0, 0, 1. We know this point is reflected onto itself because it lies on the mirror line. We've got pi over 2 and 0, and pi and -1. So we'll reflect each of these points in this mirror line. This point will be reflected to about here. This point will go over to here. We'll have the 1, 0. This point will go on the other side. And then we'll have the pi and -1 reflected to here. So if we join these points together, we'll get the graph of cos of x. So you can see that one input is mapped to multiple outputs, the positive and the negative. The same is true over here. This input is mapped to a positive and to a negative. So you can see that cos of x is not currently a function. The way we can make it into a function is if we restrict the domain of cos of x. If we only consider the values from 0 to pi, and then reflect this part of cos of x, then this will be reflected to here. So I'll remove these coordinates and this part of a curve. So if we say that f of x equals cos of x, then this has a domain between 0 and pi. So x is less than or equal to pi, but greater than or equal to 0. And the range goes from -1 to +1 within this domain. So f of x is less than or equal to 1, but greater than or equal to -1. Then we know that Arccos of x is now a function. Every element in this domain is now mapped to exactly one element in the range. So we can say that the inverse function of x, which is Arccos of x, has a domain between 1 and -1. So x is less than or equal to 1, but greater than or equal to -1. And the range goes from 0 to positive pi. So the inverse function of x is less than or equal to pi, but greater than or equal to 0. And we can see that this makes sense, because the elements in the domain of the original function are mapped to the range in the inverse function, and the elements in the range are mapped to the elements in the domain. So by restricting the domain of cos of x, we can define arccos of x as a function. In example 2, we're going to look at the arcsine of x. So in example 2, we're going to look at how and why we restrict the domain of the sine function in order to define its inverse arcsine x. You can see that the range is from -1 to +1. But if we want to define the inverse arcsine x, we need sine x to be a one-to-one function. That means for every y value, there should only be one corresponding x value. But if we look at the line y equals 0.5, you can see there are many x values that map onto this value of y. So y equals sine x as a many-to-one mapping. So when we find the inverse of this, we get a one-to-many, which is not a function. So to fix this, we need to restrict the domain of y equals sine x. And the best way of seeing how to do this is if we reflect sine x in the line y equals x. Then we'll plot its inverse. So if we choose some points on sine x, we'll have -π0, -π/2 and -1. We'll use the origin, π/2 and +1, and π0. We'll reflect each of these points through the mirror line. So this point will go through to here. This point will go to here. The origin will be reflected onto itself. We'll get π/2 and 1 reflected to this point, and π0 reflected over to here. So now we can join these points together with a smooth curve. So now you can see that this is not a function, because one x value will map onto multiple y values. The same is true on the other side. We've got this x value will map onto 1, 2 y values. And if we were to continue reflecting this curve infinitely, you could see that the x value would map on to an infinite number of y values. So to restrict the domain of sine x, we look at the values from -π/2 to +π/2. This is because the curve is increasing during this section. It's centered on the origin, and it covers the entire range from -1 to +1. And if we're only reflecting the elements in the new domain, then this is what we'll get for y equals arcsine. Just to make this clear, I'll remove what isn't reflected. So you can see that now we have y equals arcsine, which is strictly a one-to-one function. Every x value is mapped to an individual y value within this new domain, okay? So if f of x equals sine of x, then its domain is from -π/2 to +π/2, and its range, f of x, is less than or equal to +1, but greater than or equal to -1. And the inverse function of x is arcsine of x. This domain is from -1 to +1, and its range is from -π/2 to +π/2. So to summarize, sine isn't one-to-one over its full domain. We need to restrict it to between -π/2 and +π/2, and that allows us to define arcsine of x as a function. In example 3, we're going to look at arctan of x. In example 3, the purple curves represent the function y equals tan of x, which, as you can see, repeats every pi and has vertical asymptotes where the function becomes undefined. like at plus or minus pi over 2 and plus or minus 3 pi over 2. Now, just like with the sine and cosine, we can't define the inverse of this tangent across the full domain, because it's not one-to-one across all real numbers. For instance, when y equals 1, we've got multiple values x. So just like with sine and cos, within the domain of all real numbers, tan of x has a many-to-one mapping. So to define arctan of x as a function, we need to restrict the domain of y equals tan of x to an interval where it is strictly increasing and one-to-one. And we choose the domain between negative pi over 2 and positive pi over 2. Can you see it's increasing throughout this domain, it passes through the origin, and it's one-to-one. So to sketch the graph of arctan of x within this domain, we reflect this restricted portion of tan of x over the line y equals x. And the easiest way to do this is to reflect the two asymptotes. So we'll reflect when x equals pi over 2 to y equals pi over 2, and we'll reflect this one to y equals negative pi over 2. So y equals arctan of x will be the reflection in the line y equals x. So we get a smooth curve that's increasing throughout the entire domain and is centered on the origin. Now we have tan of x and arctan of x as one-to-one functions. So if tan of x is defined as a function of x, what do you think its domain and its range will be? Well, you can see its domain is from negative pi over 2 to positive pi over 2. It's not equal to these because at this point it's undefined. So x is less than pi over 2, but greater than negative pi over 2. And its range, f of x, is an element of all real numbers. You can see it shoots off to positive infinity and to negative infinity. So if this is tan of x, the inverse function of x will be arctan of x. What do you think the domain and the range of arctan of x will be? You can see the domain covers all real values of x. It shoots off to negative infinity in this direction and positive infinity in this direction. So x is an element of all real numbers. And the range goes from negative pi over 2, but it's not equal to this, and positive pi over 2, again not being equal to that. So the function y equals arctan of x is the inverse of tan of x on the restricted domain between plus or minus pi over 2. If you want more practice on this topic, you can download the worksheet and view the online lesson from my website, mrmathematics.com. I'll leave a link to that in the description below.